The moment a student sits down in a lecture hall, a wave of sensory data crashes into the tiny bottleneck of their conscious attention. Projector hums, glowing screens, spoken words, and written text all compete for the same highly restricted biological space. Modern higher education largely operates on the assumption that a teacher's job is to speak and a student's job is to listen. We share a common belief that this exchange results in the transfer of knowledge. Over decades of study, an expert builds a highly structured, intricately connected web of knowledge in their own mind. They see exactly how the individual pieces of their discipline fit together. We often expect that an expert can simply release a series of sound waves and teleport that complex web intact directly into the minds of novices. Cognitive science confirms that this transmission model is a biological failure. In 1990, Elizabeth Newton conducted a psychological experiment at Stanford University that isolated exactly why expert communication breaks down. She divided participants into tappers and listeners. Tappers were given a list of famous songs and asked to knock the rhythm onto a table using only their knuckles, while listeners tried to guess the melody. The tappers predicted the listeners would guess the song 50% of the time. The actual success rate was 2.5%. This gap defines the curse of knowledge. When a tapper hits the table, they hear the full symphony playing in their own head. They possess all the context, and they find it impossible to imagine what the rhythm sounds like to someone who doesn't. Professors operate under this exact curse. We hear the symphony of our own 30 years of context, often remaining blind to the fact that students may only hear disconnected noise. To fix this, we must examine the physical hardware of the brain through the information processing model. For decades, cognitive psychology relied on the theory that human working memory could hold roughly 7 items at a time. Recent evidence suggests that estimate was overly optimistic. Modern research by Nelson Cowan proves the actual capacity of working memory is exactly 4 items. Imagine active consciousness as a tiny cafe table. Once you place a new term, a rule, a graph, and a spoken explanation on it, the table is entirely full. When a professor adds a historical tangent or an extra condition to a math problem, they force a 5th item onto the table. One of the existing pieces of information inevitably falls off and shatters. This state of failure is cognitive overload. Data sitting in working memory vanishes after 20 seconds, unless the student expends the effort to actively process it into a long-term neural schema. A student staring blankly at the board is often experiencing a biological system crash caused by an overloaded working memory. Managing that fragile hardware requires applying John Sweller's cognitive load theory. Sweller frames attention as a fixed mental budget divided into 3 categories. Intrinsic load represents the objective difficulty of the subject. Organic chemistry simply takes up more cognitive space than basic arithmetic. Extraneous load is the useless mental friction caused by poor design. Germane load is the productive effort required to build memory. Because the budget is fixed, when extraneous load balloons, it physically crushes the germane load down to 0. Traditional lectures frequently maximize this extraneous friction. Students burn their entire mental budget just trying to decode the presentation, leaving them with no biological resources to actually understand the material.
Improving this design requires moving past the myth of learning styles. Systematic reviews show no empirical benefit to categorizing students as visual or auditory learners. Instead, Alan Paivio's theory of dual coding proves the brain processes information through 2 parallel channels: visual data through the eyes and verbal data through the ears. Placing a paragraph of text on a screen and then reading those exact words out loud triggers the redundancy effect. The brain wastes immense energy cross-referencing the written input against the spoken input, causing an immediate processing crash. Richard Mayer's rules for multimedia learning solve this through ruthless editing. Remove decorative logos, snap data labels directly onto graph lines, strip heavy text blocks off the screen, shifting that data to the spoken word. Every design choice in a slide deck directly manages the student's cognitive load. Even a streamlined, eloquent presentation carries a hidden danger. When an expert delivers a smooth, logical explanation, the student experiences an illusion of competence. They assume they grasp the concept because they are currently following the professor's neural pathways. A 2014 meta-analysis published in PNAS found that when traditional passive lectures were tested against active learning environments, the passive students experienced a 55% higher failure rate. True retention requires desirable difficulty. The physical act of building new neural connections must feel effortful and even frustrating. Educators can trigger this friction using the protege effect. By requiring students to instantly explain a concept to a peer, the brain is forced to actively structure raw data into a coherent architecture. Stepping out of the spotlight and forcing students to struggle serves a biological necessity. Even perfect initial comprehension is useless if the data decays. Hermann Ebbinghaus mapped the mathematics of memory loss in 1885. Without active intervention, 67% of newly acquired information vanishes from the brain within 24 hours. You disrupt this decay through interleaving and spaced repetition. By reconstructing old concepts weeks later and mixing different types of problems, the brain forges a permanent pathway. When the entire course hinges on a single high-stakes final, the resulting stress can physically block the prefrontal cortex. Faced with a biological shutdown and the threat of failure, students often default to the path of least resistance, cheating. The architectural solution is scaffolding. Breaking a monolithic end-of-term paper into iterative, low-stakes steps, like a bibliography in October and a rough draft in November, dissipates stress and creates a visible, verifiable process. Plagiarism and poor retention function as predictable symptoms of flawed course design. The modern university is no longer a simple repository for data transfer. Search engines and language models process facts instantly. The modern educator functions as the architect of a cognitive gymnasium. To maintain engagement, you can leverage the Zeigarnik effect. The brain naturally holds on to the tension of an unfinished task, much like a waiter who remembers a table's complex order perfectly right up until the bill is paid. Ending a session on a paradox or asking a complex question without providing the answer prevents the student's brain from closing the file on that topic. Leaving that tension unresolved is the ultimate proof that an educator understands how the human brain actually learns.